you will have the opportunity to learn, relearn, and learn that again. So don't worry about that as well. Anyway, so going to A2, right? So last time, basically, we did specific heat capacity, and we learned that basically it's really good when you draw um, the cooling and heating curves to solve these kind of problems, because these are like quite difficult in the sense that it will be confusing. So we don't want to get confused. Anyhow, today we will go further from this, and we'll see. Huh? So this time, I'd like to tell you how. Now, this part is not only required for your regular P4 questions, but this part is also required for P5, right? Now, in paper 5, if you have not started that yet, so you need to understand that drawing is an essential part in question number 1. So as I draw stuff, it also means that you guys need to learn these drawings, because in the exam, if they give you a specific question like this, then you also need to draw a detailed diagrams like these. So first experiment that we need to know is determination of specific heat capacity. Okay. Now, for this, what happens is, first of all, okay, my bad. I need to go to the next page. So I'll do that. Just give me a second. So basically, you need to have a block like this, and then you must, drill some holes in it like this. Wait, Samir, how are you? Like that. Wait a second. Then you guys need to basically, this is you need to put a, let me draw it with a different color so you guys can see. All right, then we need to put a heating element. Heating element, basically this is the symbol of an heater, and then this heater will go towards a terminal. Let's call this positive, let's call this negative terminal, and then you need to draw a switch, which is optional. If you don't do that, that's fine. And from this point onwards, you need to put a variable resistor as well. The variable resistor is required so that you can control the amount of current that flows, to make sure that any effect of heating can be minimized. Wait. All right. And then you guys need to, okay, that's pretty messed up. Chalo, koi baat nahi. Make the connection like this. So the connections are should be seen like this. So this is the circuit, and then on the other side, you need to basically put a thermometer. I'm going to label that. Let me take it to the new page, because I don't think so this space is enough for this. Wait a second. Right here. Okay. So then, all right, right here. Okay. So then what you do is you also put sort of a insulation around this block like this. And once you have basically done all this, you need to label each and everything that you've drawn. So let's do that. First of all, this would be the thermometer. You don't need to draw any thermometer, like you can just make a box and write it down, that's fine. This would be low voltage heater, because we don't want the wires outside to get hot. This is a variable resistor. This, my friends, is the supply. That's right, power supply. This would be the switch, like that. Finally, around it, this whole thing that you see is the metal block that we're interested in finding the specific capacity of, and this is the insulation. Insulation can be of any insulator like jute, wool, or whatever you want to put. That's fine. Okay. Then you guys need to write how do we find this. Okay, so please, you can draw this. It's very important. So because we put insulations, we are saying that assuming no heat is lost to the surroundings. All right. So we need to learn two things. First of all, power is voltage times current. How do we know that the voltage is there? Because we can actually put a voltmeter across the heater, and the amount of current goes will depend on the ammeter, like this. So you can measure current from the voltmeter ammeter. You can also label this if you've not drawn the current exact symbols, right? So that's fine as well. Now, because the power is being supplied by the supply, so it will have certain voltage and certain current. We can apply that to find the power. Or directly we can find the electrical energy by multiplying voltage times current and the time for which we have turned the heater on. Okay, like that. So first of all, what you're going to do is, in the first step, take the initial temperature T1. Number 2, take the final temperature T2. Then note the rise in temperature from T1 to T2 for time T. And this usually examiner would put you wants you to turn it on for 5 minutes. So that's the standard time to heat it up. Okay, you can decrease or increase it, but generally he would take 5 minutes. So you guys need to remember this. Once you've done that, then you should understand that the change in temperature is going to be T2 minus T1. M will be the mass of block taken on a electronic balance. And then what else do you need? You need energy. Energy, the electrical energy, supplied will be equal to the heat energy absorbed by the block. So this would be your Q. All right. Now, all you do then is you use the formula. You say heat capacity, specific heat capacity is given by heat energy divided by m delta theta. Whereas you can create this equation like the heat energy can be written as mc delta theta, where heat energy will be equal to voltage times current and the time for which the heater was on. Mass would be, if the mass of the block is, let's suppose you have taken m, so write m, and then c is what we need to find, and delta theta will be T2 minus T1. That is what we need. This way you can basically find the heat capacity of this particular metal block. If you have any questions, please let me know.
Sir, we don't have to add oil in the hole containing the thermometer.
No, we don't need to do that. Well,
Got
for certain experiments, we do use water for delivering like equal amount of temperature everywhere. But generally, in this experiment, because we have already covered it, and the thermometer is close to the heater, so we don't really need to do anything there. Is
All
it clear?
right.
So this method is basically when you determine specific heat capacity of solids. That's what we're doing here, right? So we have different way of taking temperatures or taking heat capacity in liquid that we're gonna look at just in a bit. All right. So please write this down. This is the main method, and obviously when we start doing paper 5, you will see that how we can implement these drawings and how do we write that. Okay. Okay. Sameer, do you understand everything? Laiba, Khatija?
Yes, sir.
Yes, sir.
Okay, good, Sameer. Every time you guys think that, okay, this is very hard for me, do let me know. I am not going to scold you at any point if you ask a question, okay? But I will be very angry if you don't speak in the class. So please speak if you have a problem, because ultimately you will face trouble if you cannot ask the question, right? Otherwise, it's good to just watch the recording if you don't want to speak. So please do, right? Okay, can I go forward now? If you guys have written this?
Yes.
Here, just 2 more minutes, please.
Okay, all right. Now, again, I'm repeating, whenever you're drawing, make sure your drawing is very well labeled. And that's something very, very important when you're doing these kind of questions, okay? In paper 4, the drawings will be given to you, but the methodology will be followed. But in paper 5, you have to draw this. So please be kind to yourself and draw nicely. Okay. Now that we have done the method for finding the heat capacity for solids, we are now going to look at how can we find this for liquids. So should I go now?
Yes.
Yes, sir.
Okay. So now please write determination of specific heat capacity for liquids. Now, for that, you need to have a setup. It's basically, let me draw this first. So, you need two thermometers in this one. Then you need basically, I don't know in chemistry what this thing is called, but it's sort of it's sort of a tube, a glass tube, where they have an inlet like this, and then on the other side we also have an outlet like
I
that.
have Liebig condenser.
Liebig condenses stuff. This is kind of different. I'm gonna show you.
Yes, it's a condenser, I think.
Yeah, it is sort of a condenser, but in physics it's not. So in this one, what we do is we put a coil. Basically, if you do not want to draw a coil, just draw a heater here. Just put like two lines, so it's a heater, and then put it like this, right, like that. Okay, and then what you guys need to do is you need to draw positive and negative terminals. You also need to draw ammeter. So to see how much current is going in, you also need to draw a voltmeter like that across this whole thing like that. Okay. All right, done. Voltmeter. Oh, and I'm sorry, I forgot something very important. You need to draw in series. You also need to draw a variable resistor. It's very important because variable resistor helps us maintain current, and we want to basically provide the constant current to this like that. All right. It also helps us to change. Now, what you guys need to do is just label this. So here you will have water in, and here you will have water out. Now, then the other things in this is thermometer. Let's call T1. Okay, and this is a thermometer. Let's call this T2. This is a again low voltage heater, because the low voltage heater is there because we don't want the central part to be super warm, like super hot, and the other parts to be colder. We want sort of a, less uncertain temperature. We want it to spread, okay, slowly everywhere. Anyway, then okay, I wanted to write variable resistor, so please write that. This is ammeter. This is voltmeter, and that would be power supply. What else do you have? Nothing else. Okay. Now you guys need to understand that, notice this type of setup is not insulated. And because it's not insulated, so there will be energy loss that we are expecting, and water is going to be flowing out. So what you guys need to understand is that water will enter at temperature T1, and when it is heated by the low voltage heater, it's going to come out with temperature T2. So we can measure those temperatures because we have put a thermometer at the entry and we have put a separate thermometer at the exit. Is it clear, everyone? Yes, Dania, you understand it? Ahmed?
Yes.
Okay, good. Now, so let's first understand what are we going to achieve. So let's write here, we are going to take two sets of readings while keeping T1 and T2 temperature constant. Now what we want is that even if we change the power of the heater, we must keep temperature 1 and temperature 2 constant. Do you guys get what I'm saying? This is our aim, okay?
Yeah.
I'll tell you why we're doing this, but you should understand this is the most important point that we need to learn. Okay, now what is really happening in this? We are basically providing the total thermal energy supplied will be equal to thermal energy gained by liquid. This is what we're going to do. On top of that, obviously, not all the thermal energy is transferred to the liquid. We also have energy lost to surroundings because it is not or cannot be completely insulated. So that's something we need to keep in mind. All right. Now, how they will basically we can go about this is that we're going to take the first reading. Let's call this reading 1. So we're going to set a voltage, we're going to set a current, all right, across it. And then we're going to turn it on for time t. Let's suppose 5 minutes, whatever time you've taken. Now, within this time, we need to understand that we must actually we must actually calculate how much mass is gonna flow through it. All right. So let's suppose m1 mass flows through it. The heat capacity of that particular material is C, and the temperature change here must be kept constant, which is T2 minus T1. And let's call the energy that is lost to the surrounding as H, that we do not exactly know how much is it. Is it clear? So
Yes.
what you guys are doing is you're sending more water or you're sending less water, and we're making sure that that basically mass, voltage and current is changed so that the temperature is kept constant. Okay, so this is the very important point. So let me just write here as well. We will change voltage, current and mass to keep T2 and T1 same, of same value. So this is our idea. Now, in the reading 2, we're gonna switch it, like we're gonna basically take another voltage, another current, and then for the same amount of time, now we would require, because if you heat something, right, if you increase the energy or power of the heater, you guys need to understand that it will basically quickly heat up the amount of water in it. But if we also increase the mass of the water that is flowing through it, so it will basically keep that, it will heat it slowly so that we make sure that T1 and T2 are same. And with that, what we going to achieve is that we will have the same amount of heat loss. Now, how is heat loss managed? Please understand this. Suppose if the temperature change in this whole system, let's suppose the temperature change, oh my God, the whole system had a temperature change of 100 degrees, let's suppose. Oh, that's too much. Let's take it 50 degrees, okay? So this was the temperature change. Now, obviously, because of this temperature, the outside temperature was, let's suppose, 30 degrees. So the heat will go out with respect to the change. This is how heat travels. It goes from higher temperature to a lower temperature, and depends on what is the difference between the temperature at one point in the room and the other. Now, in the other reading, if we manage the same, like we have changed the voltage, we have changed the current, and we have kept these two temperatures same, which means in the second reading, we will still have 50 degrees change temperature and the outside temperature is the same. So the heat that is going out as H will also be the same. Do you guys understand that?
Yes.
So that's the idea, right? Now, when you have two sets of reading, what are we going to do? We are going to subtract these two equations. So if I subtract this, you should understand V1, VI, V1, I1 and T minus V0, I0 and T. So this is the energy change will be equal to, what is this? M1, M2 minus M1. This is the change in mass. And then we have, we have C, and T2 and T1 are basically common because they're the same, so you can take the common and take the change. But interestingly, on this side, on the energy surrounding, it will be H minus H will cancel out the effect of the loss of energy that is happening here. So then you will be able to remove the energy that is lost to the surroundings, and then you will be able to get the most accurate value of heat capacity of a liquid. Is it clear, everyone?
Yes.
So this will be delta Q MC delta theta. So this is how it's basically taken. Okay. Please write this down, draw the whole thing, and then we'll see what kind of questions do we expect in the exam as well. Okay. All right. Can I go forward now? तुम क्लास में ले रहे हो क्लास में ले रहे अच्छा yes please can I go forward now everybody's written this
Yes.
Yes, sir.
okay cool now let's see what kind of problems we will face okay let's put it here go to the new page yes my friend good one. Oh, my bad. Sorry. Yes. Where are you, A2? Where are you? All right. Okay, this is something else. This is for the next one. Let me fill up this. Wait a second. Why? Okay, got it. Let's see. So this is the kind of diagram that we've just drawn. So they've drawn it in 3D. It doesn't really matter. We're gonna skip this because this is not required. Anyway, we're gonna start with this. Okay. Um, so in this one, all right. Let's copy this. I'm gonna put it into new page because I want the first question first. Like that. let's go forward. Okay, this is the sort of question that we just did, so that's fine. We need to take the first question out. Okay, let's copy it till here. It's fair enough. Okay, let's put it back. Like that. Okay. Now, okay, I took a very long screenshot. That's not bad. Make it smaller. Let's put it here. Okay. Now, let's have a look. In the very first question, as you guys can see here, it says a thermometer and electrical heater inserted into holes in an aluminum block of mass 960 kilograms. Like I said, they're going to give you the mass here. Then they say, there's connection to electrical circuit. There's a heater, blah blah blah, and the power of the heater is 54 watt, as you guys can see as well. Now, today, where is Abu Bakr? Abu Bakr is not here today. Why? Okay, anyway. Now going to the next, it says the heater is switched on and the readings of temperature of the blocks are taken at regular time intervals. When the block reaches a constant temperature, the heater is switched off and then further temperature readings are taken. The variation with time t of block is shown like this. Okay, fair enough. So this is temperature and this is time t. Okay. Then in the next, it says why the rate of rise of temperature block decreases to 0. Now, what you guys need to understand is, in our diagram, we put insulation to keep the temperature maintained, but in this one, as you can see, there is no insulation. So nobody's going to tell you in this. You just need to look at the diagram to understand that why it is happening. So we're going to say, for 2 marks, we're going to write that this is because the heat is transferred to the surroundings. So this should be your first point. And then they say in the text they've written, we wait when the temperature is constant. So when the block reaches constant temperature, how can temperature be constant? Temperature can only be constant when the heat that is coming in is also going out. So then the temperature will not rise. So we're going to say that temperature becomes constant when energy in is equal to energy out. Is it clear, everyone? Any questions here?
No.
So please try to see it from the examiner point of view, what he's doing, and check out the drawing very clearly. Clear? Samir, do you understand everything? And Eon and Javelia?
Yes.
Okay. Then it says after the heater has been switched off, the maximum rate of fall of temperature is 3.7 kelvins per minute. So we already know that the change in temperature is 3.7 Kelvin and the time of its fall is 60 seconds because it says 3.7 kelvins per minute. Is it clear, everyone? So when the temperature was constant, we've already written here that the input energy was equal to the output energy. So the input energy was coming from the power of the heater, which was, I think, given somewhere, which is 54. So what I'm going to do is I'm going to write it as power was 54. I want energy, so I'm going to multiply 60 seconds along with it because I want to find the energy. Is it clear? So I've done power into time if you do not understand this. Is it clear? Then the output energy is basically when it is going in mc delta theta. So let's write the whole equation. 54 times 60. The mass was, I think, 960. I think 960. Yeah. So it's going to be 0.96. This is heat capacity, which is going to be C, and this is going to be 3.7. Right. So then 54 times 60 divided by 0.96 divided by 3.7, and the heat capacity comes out to be 912 joules per kg per Kelvin. Any questions here? Please let me know. Okay. So everyone amongst you understand this? Should I go forward now to the next question?
Yes.
Okay. The next thing is this type of question. Now, the first thing they're asking you is what exactly do you mean by thermal equilibrium? We have already done this before in the temperature chapter, and we would like to answer it as that thermal equilibrium is thermal equilibrium is the temperature of two bodies in contact when there is no net. Now, writing this is the keyword. You won't get the other mark if you don't write this. Net transfer of heat between the bodies. Now they have written metal spheres, so I'm sorry, I wrote metal spheres, so I'm going to write temperature of two metal, I did not see that, spheres in contact, right? So basically writing this part gives you 1 mark, writing this part gives you the second mark. Is it clear, everyone?
Don't we have to mention that they have equal temperature?
Yes. Yes. So when you write thermal equilibrium is the temperature of two bodies, so you can write equal temperature, that's fine. Is it
Okay.
clear? So the net flow will be 0 when they reach equal temperature. Like I said in the previous one, here you might have seen, I told you that if there's a change in temperature, like this is 50 degrees, this is 30 degrees outside, so temperature basically causes heat to go from higher to lower. If this was 50 and this was also 50, then basically there will be no net flow. Do you get my point?
Yes.
That's fine. So this is what they're asking. Actually, then next, this is the similar diagram that we've just done. They just used coiled heating element, but that's fine. Now it says an electric water heater contains a tube through which water flows at constant rate. The water in the tube passes over a heating coil as shown. The water flows in the tube at a temperature of 18 degrees. So it means at this point there is 18 degrees, and when the power of the heater is 3.8, the temperature water outlet is 42 degrees. So this is the temperature change happening. It says the specific heat capacity of water is this. Use the data to calculate the flow rate, which is mass per unit time. So they're asking about mass over time, grams per second, of the water through the tube, right? Now, what do we need to understand? We need to understand that the power of heater would be equal to the power delivered in heating water or whatever that is, right? I think it's water. Okay, fine. So the power of heater is given as 3.8 kilowatt, which is 10 raised to power 3, like that. We want to find the mass flow rate. So mass flow rate basically means mass over time. So basically, let me just explain this this way. So what we are basically achieving here is that power itself is energy over time. So this whole thing is energy, and we're dividing it with time, right? So energy comes off as mass times heat capacity times change in theta over time t. So this is power. Okay. The same thing you can also multiply t here to find the energy and divide t later on. That's fine as well. So let me just write the way we were doing, because then you guys won't be confused. Wait. So we can say energy supplied by heater will be equal to energy gained by water. Alright, so energy equations are basically power into time is energy. Here energy will be mc delta theta. We want mass over time, so we're going to take time on that side. So it will be mass over time times c times delta theta. Any issues here? Anyone who could not understand this, please let me know. Or subsequently you can do directly, it's up to you. So the power was 3.8 times 10 raised to a 3. We want to find the mass flow rate. The good thing is this is in grams, so we don't need to change anything. 4.2 directly. And the change in temperature is 42 degrees minus 18. You guys get it? Can somebody please help me find the mass flow rate here? Yes, please. Yes?
Final answer 37.7.
37.7?
Yes.
So that would be 38 grams per second, two significant figures, right? Now, in the next thing, it says explain whether your answer is likely to be an overestimate or an underestimate of flow rate. Now, please understand this. If you check out the drawing, does it have insulation on it?
No.
So what we have missed in this?
That the energy supplied by the heater should be equal to both energy gained by water and energy lost to surroundings.
It means
So
that he did
the
not
actual
ask
flow rate
about
should be less.
yes. So we have missed the energy that was gone to the surrounding. We have not taken that into account. So will this value that we have calculated would be higher or lower?
Higher.
Higher. The reason is that we have basically higher means that actually in reality it should have been the energy, which is power into time, should have been subtracted from h, that we haven't done. So it means this is an overestimate. So I'm going to say that some thermal energy must be lost to the surroundings. So it is an overestimate. Is it clear, everyone?
Yes.
Yes, Amna, Dania, Ahmed, you guys
Yes.
understand? Okay. And Afan, Eon, Khatija. Where's the other Khatija? She's not here today.
No problem from my side.
Okay. Laiba and Javeri and Sameer, everything is clear?
Yes, sir.
Okay, that's good to know. So today, basically, these are the type of questions. They keep on repeating the same question, same question. So if you have a topical book, if you do not have a topical book, that's fine. I'm gonna share you the link. You can also practice that on your own. Okay, so I'm gonna put it here actually, and then you can basically practice these questions on your own and get back to me if you do not understand something before I give you an assignment myself once this is completed. Okay, so just hold on. I think my topical was. Let me check. What is this? Okay, so thermodynamics. So let me give you the full book instead of these worksheets. That's better. Okay, so we're looking at paper 4. Where is it? All right, this one. Let me check what is the access level to this. Anyone with the link? Okay, I'm putting it on Google Classroom. Please make sure that you guys actively do these questions, because in A2 the biggest difference between AS and A2 is that A2 is like multiple folds of chapters within one chapter. So if you keep on practicing small parts in each chapter, I think you won't be able to lose any marks then. Okay, so you guys need to download this. This is the topical for A2. Okay, and just go into thermodynamics and find the questions that we've done today and just practice them. All right, is it clear, everyone? I think that would be
Yes.
for today then. Have a nice day.
Thank
All right,
you.
sir.
Bye.
Allah.
Assalamualaikum, sir.